Greetings, ladies and gents, and welcome back at St. Mike Maths and Science Club. Today we will be looking at electric circuits. This is actually the first, topic in this, videos that I'm making. Of course, on the physics side. So I've been, looking at, the math side alone. So I just thought that, I must, let me just go to the physics side, and just thought that maybe I should start with electric circuits. So today we'll be looking at, of course, a revision from the things that we did last year. So of course, so this would be just the revision. We're going to I'm going to produce another video, of course, looking at the things of course that you're going to encounter in grade 12. Of course, things that involves internal resistance, but we're just going to look at that in the next video. So of course, last year we should have learned that, of course. So if of course you look at this diagram, of course this is a circuit, and we know that of course we have an ammeter, right? I'm just gonna do a recap, of course, at the the things that of course that we find in a circuit. So of course that of course we have an ammeter, and we know that, of course, an ammeter in this case it reads the current that is passing through its certain conductor in a sense. And of course we also have a resistor. So this in a sense would be a sort of a resistor. So and remember that, of course, current is measured in amperes. So of course you must be able to know that. And of course we know that, of course, the resistance or the resistors, of course, in this case, are measured in ohms. So this in a sense would be a resistor. I'm just going to denote that as resistor R1, and of course that is R2, and that is R3. And of course we know that that is the battery. Of course, the battery, it provides us with a certain voltage that, of course, we can use. Of course, that will be, of course, distributed to our our circuit. But as you can note in this diagram that we have here, so this as you can note that, of course, these resistors that I have in this circuit are actually in series with one another, meaning that of course, now remember, in grade 11 you learned that, of course, resistors that are in series, of course, they have the same current. So in this case, the current that, of course, comes out of the battery, if you think about it, would be the same current that would be, of course, passing at resistor 1. But at the same time, it would be, of course, the same it would be the same current that would also be passing at what, at R2 and, of course, R3. So in this case, we know that, of course, resistors in series, they, of course, they have the same current. So that's the first thing that you must note. I'm just going to write that down. So our resistors in a series, you must note. So the first thing that you need to note is that they have the same current. So that's the first thing that you need to note. And of course, the second thing that you need to note is that resistors in that are in series, they divide the voltage. So in this case, of course, now suppose we had a certain voltage that is supplied by the battery. I'm just gonna take a certain bit. I'm just gonna take 12. So suppose, of course, that battery was supplying us with 12 volts. Now what you need to notice that, of course, now remember I said that resistors that are in series, they divide the voltage, right? Meaning that some of the voltage that, of course, will be supplied by that battery will be used at R1, and some of it will be, of course, used at R2, and of course the what's left will be, of course, used at R3. So what you need to note, of course, is that resistors in series, of course, they divide the voltage. They actually, the voltage are dividers, so they divide the voltage. So that's one thing that you need to note. And of course, now remember, in grade 11 you should have learned that of course we can actually take you can actually take all of these resistors that we have and make them treat them as one. Now remember, if of course you are trying to calculate the total resistance, this is of course when you're taking the sum of all of those resistors, right, combining them into one. So of course, if you are looking, if you're trying to calculate the equivalent resistance, that's the word that they normally use. So in this case, to calculate, the sum of all of this resistance, you would actually R series. You take, of course, the first resistor, R1, plus R2 plus R3 until of course to the end, of course if there are many more there. So that's of course the way you would the way you would you would use to calculate of course the resistors that are in series with one another. So you just take R1 plus R2 plus R3, and of course until of course if you have of course the fourth resistor, you of course say plus of course the third resistor. So another thing that you must note, now remember we said of course a battery supplies us with a certain voltage, right? So some of it of course will be used by this one, by R1, and of course some of it will be used by R3. So what you need to note is that whatever the energy whatever voltage that the battery supplies us with, that voltage will be used, some of it will be used at R1 and some of it will be used at R2, and of course what's left will be used at R3. So in a sense we would of course come with a certain formula that says of course V total. Now remember this would be of course the total voltage that is supplied by the battery, right? But that voltage in this case, it will be the total voltage, right? But that voltage of course would be of course shared to R1, so it would be of course equals to V R1 plus of course VR R2 plus of course V R3. So it would be shared of course throughout those three resistors. So that's that's one thing that you must note. So of course when it comes of course to that second diagram that I have on the left, so if you note, now remember of course you must know that when we look at those terminal those stuff that we have there, so what you need to note is that of course the current in this case always flows from the positive terminal to the negative terminal. So the one that has a longer tail is actually represented as the positive terminal, and of course the one that has a shorter tail is it's always, you can denote that as the negative. So we know that of course you should remember that of course the current flows from the positive terminal of course to the negative terminal. So in a sense the current that comes of course that comes out of the battery would be I total, right? So this would be of course the total current. So in this case the current that will be passing at at ammeter A1 in this case would also be the total current. So of course that would be the total current, and of course the current that will be passing of course at A2 of course at that point would also be the total current in our circuits. So that's one thing that you must note. Of course there's something else that I'm gonna mention that's very important, but of course if we look at the second diagram that we have there, of course this would be of course the voltage that is supplied by the battery, right? So again a battery supplies us with a certain voltage. Again that voltage would be distributed at that resistor. I'm just gonna call that of course again R1. So I'm gonna write that as R2, R3, I'm going to note that is R4. So what you need to note, of course, when you look at this diagram, is you can note that these are resistors that we have down here, they're actually parallel to one another, right? So one thing that you must note with resistors that are parallel is that they actually they have the same voltage. So if you know the voltage across this across this branch, you would actually know the voltage also across this branch here. But what you need to note is that of course R4 in this case is not parallel to R3 alone, but that R4, that resistor there, is actually parallel to both of these resistors when combined in one. Now remember we can actually treat that as one by taking of course R1 plus R of course by taking R2 plus R3, of course treating them as one. So what you need to notice that these two resistors are actually parallel to this R4. So that's one thing that you must note. So again, we can choose to write to draw that differently. So in this case, this is of course when we combine these two resistors. So before I even get there, so one thing of course you must note by resistors that are parallel to one another is that they have the same voltage. So resistors that are parallel, they actually they have, so the first thing that you must notice that they have the same voltage. So that's one thing that you must note. So in this case, if you know, of course, the voltage across the, the R4, you would actually be able to know the voltage across, R3 and R4. So that's the first thing that you must note. And the second thing that you must note is that of course, the resistors that are in parallel, they actually divide the current. They're actually, current dividers. So in this case, the resistors in that are parallel to one another, they divide the current. As you can notice, just as you can note that of course resistors that are in series, they have the same current, but the one that are parallel to one another, they actually divided. As you can see that it's actually kind of switched the other way around. So of course, so that's the second thing that you need to note. Now remember, we said of course the current that comes out of the battery would be I total, right? So in this case, the current that that ammeter there would be reading, it would be of course I total. So that's one thing that you must note. And of course, the current that would be of course passing at R1 would be the total current. But when it gets to this node here, this is when of course your current splits. So some of the current would be of course traveling that direction. So I'm just gonna call that I1, and of course some of the current of course would be traveling that direction there. So I'm just gonna call that I2. So that's one thing that you must note, that of course resistors that are parallel to one another, they divide the current. So that of course at that node would have of course the total current, right? But immediately when you pass that node there, some of the current would split, go to that branch, and of course some of it would travel through that branch. So one thing, of course, now remember we said of course resistors that are in series, they have the same current, right? So of course if we know that that resistor has a current of I2, so of course we'll be able to note that of course the R3 in this case would have the same current. Why? Because of course they are in series with one another. So I'm only talking about these two resistors, right? So that's of course the second thing that you must note. But remember, we said of course when it gets to that, when current gets to that node, this is where it splits, right? So it will split to I1, and it will also split to I2. But however, when it gets to this node here, this is when of course it kind of come back together and join it, and of course to become one another, to become one unit. So when of course, now remember that branch would have I1, and there would have I2. So of course when we get to that node, this is where of course I1 and I2 become one again. And of course, so the current that would be passing that ammeter there, of course that would be the total current. So that's one thing that you need to note. And of course, now remember in grade 11, I'm sure you learned but before I even got there, I'm actually thinking ahead a little bit. So of course the third thing that you must note, that of course when we calculate the resistors that are parallel to one another, we use of course the formula 1 over R parallel is equals to 1 over R1 plus 1 over R2 plus of course 1 over R3, and of course so on and so forth. So that's one. So that's the formula that we use. Now I like to modify. There's a way. I actually modify this formula. I actually change it to R parallel, being of course 1 over R1 plus 1 over R2 plus 1 over R3. And of course I just put a negative 1 up there, so it kind of invert it. But that's of course that's another way we can choose to write that formula. Of course it's the same thing at the end of the day, because in this case after you have done your calculation, what you do is that you would actually invert that value that you get, right, the other way around. So immediately what it does is that it actually invert it for you immediately. So that's of course the other way that you can use to calculate resistors that are parallel to one another. But nonetheless it's still the same thing. So again another thing that you should have learned is that, now remember we said of course the current when it gets to that node, we said it splits to I1, right, and I2. So what we can note about that, now remember the current that was here in this case would be I total, right? So in a sense I1, when I take the I1 plus I2, I must always get of course the total current. So of course I1, of course that total current in a sense between, and I'm only looking at those two branches, this would actually be equals to I1 plus I2. I hope that makes sense. Now remember, when current gets to that point, this is when it splits, right? So of course it will split, going some of it going that direction, and some of it, going that direction. But when I add those two currents, in a sense, they will actually give me the total current. So that's one thing that you must note. And of course, in grade 11, you should have learned of the Ohm's law. Now I don't want to go. I don't want to stay too much on the revision part. So I don't want to make this video the longest, that's why. So one thing that you, of course, you learned in grade 11 is that, of course, we have a law, of course, the Ohm's law, which states that the potential difference across a conductor is directly proportional to the current in the conductor at constant temperature. So of course we have a formula that, of course, that evolves around that idea. Of course, that says, of course, R in this case is equals to V divided by I. So that's Ohm's law. So that's it's given, of course, in the formula sheet. So one thing that of course I must say is that, now remember, we said, now remember at this, let me just take that one. So of course the voltage, so remember we said, of course, some of the voltage that, of course, is supplied by the battery would be used, of course, by R1, right? And some of it would be, of course, used by R2 and R3. So one important thing that I must say, and that you need to note, is that whenever you are using this law, Ohm's law, is that whenever, so when you take a certain voltage, now suppose you are decide to take the voltage across, of course, R1 in this case. So what you need to note now, let me just modify this formula again. So I'm just gonna take the current as the subject of the formula. So this would be, of course, equals to V divided by R. So one thing that you must notice that whenever you choose to take to use a certain voltage, you must always use it with its corresponding resistance. So if you choose to use, of course, V1, and I was suppose, of course, we had a certain voltage there, let's say V, I'm just going to call that V1. So of course, if you are going to use the voltage across that resistance, you must always, of course, use that resistor, because now remember that that voltmeter there would be reading the voltage across that R1. So if, of course, you're using that V1, you must always use it with its corresponding resistor. That's one thing that you must note. Now suppose, of course, you were calculating the current across that resistor. So of course, if you have the voltage, in this case, you would need to use that resistor there, not any resistor, but R1. So that's one important thing that you need to note. And again, if, of course, you choose to use V in this case, now remember, this of course would be the total voltage, right, that is supplied by the battery. So if you choose to use that voltage there, you would actually, now remember, this would be V total, right? So that's the total voltage that, of course, is supplied by the battery, right? So if you use a V total, you must also use the total resistance, meaning that, of course, if we look at that, so if you use V total, and remember that's V total, right there. So if you use that V, that 12 volts, you would need to use, of course, R1 plus R2 plus R3. Now remember that, of course, that voltage there, or voltmeter, in a sense, would be reading the voltage that is shared to our external external circuit. So if you choose to use that V, you would need to use it with its corresponding resistance. So one thing you need to note is that voltmeter, they would be reading the voltage that is distributed to these three resistance. So if you use that 12 volts, you would need to use it with its corresponding resistance, which would be, of course, R1 and, of course, R2 and R3, of course, combined. So that's, of course, that's the most important thing that I can say at the moment. So without dragging this, let's just look at questions, of course, that I've provided, and of course we just if, of course, there's something else that I can add, I can just add it as time goes. So we're going to look at one question. Let me just take those papers off. So of course, if you look at question 1, so I need you to to keep in mind of the things that I've mentioned, of course, on that I've mentioned, of course, for the resistors that are in series and also for the resistors that are in parallel. Now again, I just made random questions, of course, evolving this idea of resistors that are in series. Of course, they're going to get tougher and tougher as the time progresses. So if we look at question 1, they say that the battery in the diagram below has an EMF of 15 volts. So in this case, the word EMF in this case would be the total voltage that that is actually supplied by the battery. That's of course in grade 11. Of course, in grade 12, things kind of change a little bit. But anyway, let's not go there for now. So of course, so they say that of course that the battery in the diagram below has an EM of 15 volts. So again, you can note that of course this would be of course the voltage that is actually distributed to our external circuit, right? But remember, of course, we said that the current always flows from of course the positive charge. So of course you can see that this side is a longer tail. So this of course would be the positive terminal, and of course that would be the negative terminal. So again, now remember we said of course the current that comes through out of the battery would be of course total current. So in this case, the current that will be passing through that ammeter there would be the total current. So that's the one thing that you must note. Of course, that would be of course I total passing through there. And of course, even when it gets to that 3 ohm resistor there, we would have the total current. So if we look at question at 1.1, they say that calculate of course the total resistance in our circuits. So what they want is that they want the equivalent resistance, the sum of all of these resistors when combined. So when combined, of course, so to do this, we would say of course R series. We can note of course that this resistor is in parallel to the is actually in series with that 5 ohm resistor, and also it is of course in series with that 12 ohm resistor. So in this case, we would note that of course 7. So in this case, to calculate R series, we would take of course R1 plus R2 plus of course R3. Now of course R1 in this case would be 7 ohms, so that would be 7 plus that 5 and plus of course that 12 ohm resistors. And of course, if you put all of that together, you're going to get 24 ohms. So that would be of course the equivalent resistance in our circuit. So this is when we take all of those resistors and we treat them as one. So that of course would be 24, not actually 2. So the second question, they said that calculate the total current passing through the circuit. Now remember, now one thing of course that I forgot to mention, whenever of course now every point that of course the most important thing that you need to know is that every point must have 3 information. So if we look if we take that 7 ohm resistor, so in a sense we must know at that point we must know the current that is passing through that resistor. And the second thing, we must of course at that point we can be able to determine the voltage. And of course also we can be of course the resistor in this case would be of course 7. So of course at any point there is resistance, all right, there is also voltage, and of course there is also there's also current. So that's one thing that you must know. Now they say that calculate of course the total current passing through the circuit. So they want of course the total current that is passing through our circuit. So if we so of course to calculate that, now remember they gave us the voltage across our battery, right? So of course we know that there is of course a formula, Ohm's laws formula, which says of course I is equals to a V over R. So now remember they say they want the total current. So in a sense, what I'm going to do now, remember what I'm given there, if I check in my diagram, I'm given that 15 volts, right? But that 15 volts would be the voltage that is actually distributed to our external circuits, right? But that voltmeter there, of course that voltmeter V1, they would be reading the voltage that is distributed to that 12 ohm resistor, plus of course that 5 and of course that 7 ohm resistor. So if I choose to use that 15 volts, I must use it with its corresponding resistance. all right, or resistors. So if I, of course, I choose to use, that 15 volts, I must, of course, use also that of course, the resistance in this case must be 12 plus that 5 plus that 7, because that voltage there is actually the voltage that is distributed to external to our circuits, right? So of course, to calculate I in this case, what I'm going to do is that, of course, I'm going to take V. Now remember that I'm going to take that 15 volts, so this would be 15 divide by, now since I took that 15 volts, I must also take its corresponding resistance, right? So in this case, we know that, of course, the resistance that is that corresponds with that 15 volts would be, of course, R1. It would be, of course, that 12 ohm resistance, and of course that 5, and of course that 7 ohm resistor, because that 15 ohm is, of course, the voltage that is distributed to that 12, and of course that 5 ohm, and of course that 7. So in this case, that would actually be divided by 24, and of course, if you put that in your calculator, you're going to get 0.25, and of course, if you round that off, you're going to get 0.63. so this actually be 0.63 amperes. Now remember that, of course, the current would be is measured in amperes. So of course, if we look at question 1.1.3, they say that calculate the reading on V2. So they want the voltage across the 7 ohm resistor. Now again, since we want, of course, the voltage, and now remember, at any point we must have, of course, there are always three information. There is a current, there is voltage, and also there is, of course, the resistance of the resistor, of course, of the resistance. I don't know which way around, but anyway. So of course, if we check at that point, all right, they want, of course, the voltage, right, across that 7 ohm resistor. So what I'm going to do, since, of course, I'm looking for the voltage, I'm going to use Ohm's law, of which says, of course, I, this case is V over R. But remember, I'm looking for the voltage across that 7 ohm resistor, right? That 7 ohm resistor. I hope that's visible. And of course, that R that I'm going to use in this case would be that 7 ohm, right? So this would be, of course, that 7 ohm. Now remember, I'm looking for the voltage across that that resistor, right? But remember, which current would be passing in that 7 ohm resistor? It would actually be the total current, because in this case, it has, and there is no branch that actually splitted the current, right? So in this case, I at that point would actually be that 0.63. So that's one thing that you must note. And of course, we know that the resistor there would be, of course, 7 ohm, and of course, what we are looking for there would be the voltage. So of course, what I'm going to substitute my values, and of course, the current across that point would be 0.63. that would be equals to V. That's what I'm looking for, right? And of course, the resistor would be 7. And of course, if you cross multiply, you're going to get the value for V, of course, the voltage across that point. That 7 ohm resistor is a 4.38 volts. So that would be, of course, the voltage that is used across that 7 ohm resistor. And of course, if you want to find, of course, again, the voltage that across that 5 ohm resistor, you would do the same thing. Again, we know that, of course, the current that passes through that 5 ohm resistor would be the total current, right? So it would also be that 0.63, and again, it would be the same current that passes, of course, that 12 ohm resistor. And again, so you can actually use the same approach to find that those the voltage across each of those resistors. But what you need to note is that, of course, now remember, we found that to be 0.38, right? So if you calculate the voltage across that 5 ohm resistor, of course, using the same law, and of course you calculate that the voltage across that 12 ohm resistor, if you add all of those voltage, you will find out actually that they are all they would actually be equals to 15. Now, of course, that would make sense, because that 15 ohm that 15 volts would be, of course, distributed to that 7. It would also be distributed to that, and of course it would be distributed to that 12 ohm, and of course that's where it would end. So that's it for question 1. So we're going to look at another question, which is question 2. So question 2, again, So this would be, of course, the questions that we're going to do. Again, I can suggest that, of course, you pause, of course, since it's a revision, and of course you try the question, and of course you can watch the solution. So these will be the questions that we're going to be working through. So they said that the battery in the circuit diagram below has an EMF of 14 volts. They said that switch S is closed. Now, of course, one thing that I didn't mention, ladies and gents, is that, of course, when the switch is open, there will be no current that is passing through at that point. But immediately when, of course, the switch is closed, this is, of course, when your current starts to flow. So that's one thing that you must know. So they said, of course, that switch S is closed. So meaning that, of course, there will be current passing through that point, of course, to that 3 ohm resistance, of course, until of course to those two resistors that that are parallel to one another. So if we check the question, they say that calculate the total resistance of the circuit. Now if you remember again, we said, now remember to find the total resistance. In this case, we'll take this resistor, all right. We of course we add it to the of course the resistance to these two resistance. Now the first thing that you need to do, of course, would be to calculate the equivalent resistance of these two resistors that are parallel to one another. So of course you're going to use the formula. Let me just start here. So of course, to calculate so the first thing that you must note is that, of course, to calculate the equivalent resistance across our circuit, so we would need to know the R parallel. So of course we would need to calculate R parallel, and in this case we would add it to that 3 ohm resistor. So when, of course, we calculate R parallel, we would in a sense be combining these two these resistors that are parallel to one another and treat them as one. So of course what you're going to do is first going to calculate my R parallel, and when I get that R parallel, I'm going to add that 3 ohm resistor, because in a sense, so if of course I decide to redraw that circuit there, I would actually have, now I'm gonna neglect the other stuff. I'm only just gonna focus on these two. So if I calculate the equivalent resistance across these two across these 3 parallel resistance, so what I'm going to get is that I'm actually going to treat them as one resistor. So in a sense, this would be, of course, that R1, this R 6 ohm resistor, and that, of course, when I calculate R parallel, so this would actually be R parallel, and of course now it would actually be in series with that 3 ohm resistor. So of course what I'm going to do first, I'm going to calculate my R parallel, and in this case it would so immediately after that it would be, of course, in series with that 3 ohm resistor. So what I'm going to do is that I'm going to say, of course, I'm just going to write that down there. So what I'm going to do first, I'm going to calculate my R parallel again. So we know that, of course, R to calculate the resistance that are parallel to one another, we use, of course, 1 over R parallel would be equals to 1 over R1 plus 1 over R2 plus, of course, R3, and of course, and so forth and so on. But what you need to note is that when we calculate R parallel, the first thing that we do is that we're going to combine these two, treat them as one, because they're in series with one another, right? So of course, if you modify that, this would actually be 1 over that 6 ohm resistor, right? That's 6 plus 1 over that R4 plus that 8. So that would be, of course, when I'm calculating my R parallel. So of course what I'm going to do, that this would be 1 over 6 plus 1 over, we know that 4 plus 8, that would give us a 12, right? So this would be, of course, a 1 over 12. So this would be my 1 over R parallel. So again, to calculate R parallel, what I'm going to do, I'm going to use the technique for saying R parallel in this case would be equals to 1 over 6 plus 1 over 12, and of course we put a -1 there so that it invert it for us. So what you're going to get there, you're going to get R parallel being actually the 4 ohm. So we're going to have a 4 ohm there is our R parallel. So that would actually be my 4 ohm resistor there. So this is, of course, when I combine this branch with that branch there. So of course, now remember they said that calculate the total resistance in the circuit. So in this case, immediately after I calculated my R parallel, so that would be of course in series with that 3 ohm resistor, right? So of course, to calculate R total, so that would be of course the total resistance in our circuit. So that would be of course R parallel plus that resistor that it is in series with. So this would actually be of course 4 ohm, 4 plus 33, and of course what you're going to get there would actually be 7 ohms. So that would be of course the total resistance in of course of the circuit. So what I'm going to do is that just going to write that down. So we found that that of course our R total was equals to that was equals to 7 ohm. So we're going to to write other stuff, of course, in that in this paper. So of course, the second question, this they said that calculate the reading on the ammeter. Now again, we know that we can note that of course that voltage there that is distributed. They said that that's 14 volts, right? So now they're saying that calculate the reading on the ammeter. So this is our ammeter there. Now remember an ammeter, it reads the current, right? So what they're asking us there is that they're asking for us to calculate that the current that is read of course on that on that ammeter there. Now of course, to calculate total current, of course what we're going to now remember, if we can look at the information that they gave us, they only gave us that 14 volts, right? So again, if I use that 14 volts there, I would need to use it with its corresponding resistance. All right, now so of course we would need to use it with this corresponding resistance. Now again, if I ask of course which current or which of course which resistors of course would be using that 14 volts. So in this case, it would be this resistor, of course, plus this 3. Now remember, of course, we kind of combined these two, and we found that of course the equivalent resistance, of course, across our parallel resistors was actually 4 ohms. So what I'm going to do now to calculate I, I'm going to say I again is equals to V, of course, divide by R. But again, of course, if we check at the information that they gave us, they actually gave us 14 volts, right? So of course, so now remember, that's actually V total, right? That's it would be the total voltage. So of course, if I'm going to use V total, I must also use R total, right? So that would actually equals to what to our total current. So that's of course our total voltage in this case. They gave us to be 14, right? So this would be of course 14, and of course our total resistance in our circuit, we found that to be 7. So this would actually be divided by 7. So in this case, if you put that in your calculator, you're going to get a value of 2. So that would actually be 2 amperes. So that would be of course the total current. So that would be of course the current that is read by that resistor that we have there. So they say that calculate the voltage across the parallel resistance. Now again, of course, now remember, if we of course combine, and now remember we combined this resistors, right? And then we found that to be, let me just write there, just hope I'm not gonna run out of space. We combined those two branches there, and we found that to be 4 ohm, right? So that was actually our R parallel. So what they're asking there is that they're asking us to calculate the voltage across our parallel resistance. But of course we know that of course our parallel of course they say that calculate the voltage across our parallel resistance. But again, now remember we said of course at any given point we must we have 3 informations, right? We have the current, we have the voltage, and we also have the resistance, right? So of course if we are trying to calculate R parallel, right? So of course we are going to use the same formula, Ohm's law, which says of course I is equals to that V divided by R. But remember, what am I looking for? I'm actually looking for V parallel, right? So I'm actually looking for the voltage across our parallel resistor. So which of course, now remember, if I'm calculating of course V parallel, in this case I must also use R parallel, right? Because we said of course when you use a certain voltage, or you must use it with its corresponding resistor, right? So in this case, so even with that I, it would be of course I parallel. Now if you note, so this, now remember this was of course our parallel resistor, right? So if you note, now remember we said of course the current that would be coming through out of the circuit would be of course the total current, so it would be of course the same current that passes through that point. So of course if we combine those two resistors, the current that will be passing through that point would actually be I total, because now remember we've treated it, them as one, so in this case they're in series, right? So in this case the current that will be passing through that are parallel would actually be I total. Now remember we found I total to be of course 2 amperes, so what I'm going to substitute there would actually be 2, and of course I'm looking for V parallel, so in this case V parallel, of course I'm going to divide that by R parallel, and then we found that R parallel to be 4. So of course V parallel would actually, now if I do my mathematical gymnastics, so of course if you do a cross multiplication there, you would actually find that to be 8 volts. So that would be of course the voltage that is used across my parallel resistance. So of course in this case, now remember we said of course resistors that are parallel, they have the same voltage, right? So in a sense, of course, we would be able to note the voltage across this of course across the 4 ohm resistor, and of course we would able to know now we would actually be able to know the voltage across these two resistance when combined. So of course if we now remember we found the V parallel to be 8 volts, right? So of course we would be able to know that of course the voltage that is passing through this parallel resistors would actually be 8 volts. So if of course our V parallel is 8 volts, that would actually mean that of course the voltage across those two would be 8 volts, and of course that would also be 8 volts. So we're actually treating them as one. So these two branches would actually be using 8 volts. So I would know. So if of course if we check at the fourth question 2.4, they said that calculate the current that is passing through our 6 ohm resistor. Now remember we said that of course resistors that are parallel to one another, they use the same voltage, right? So in a sense we would be able to know the voltage across this branch. So it would actually be what? It would actually be 8 volts. So in this case, if I'm calculating the current across that 6 ohm resistor, again I'm going to use Ohm's law. So of course you know that I is equals to V divided by R. Now since I'm looking for the current across that 6 ohm resistor, now remember I know the voltage that across that branch, right, to be of course 8 volts. So now remember, now I'm looking for the current. So in this case my voltage in this case would be that 8 volts, and of course my my resistor would be that 6. So in this case if you take 6, if of course you take that 8, you divide that by 6, you're going to get a value of 1.33. So you're going to find the voltage, the current rather, across that 6 ohm resistor to be 1.33. So that would be of course the current that is passing through that 6 ohm resistor. So that of course would be for question 2.4. I hope I hope it's helping at some extent. So this was actually question 2.2. So this was actually question 2.2. Of course this was actually at 2.3. So that was actually 2.3 there. So of course what we're going to do again, we're going to look at another question, which is actually question 7, which is actually a question that I sourced from one of the past exams that was written. So of course if we look at the statement again, they say that in the circuit diagram below, the voltage across the cell is actually 12 volts. So again we can note that of course this would be of course the positive terminal, right? Of course, so our current in this case would be traveling in that direction. So we would have of course I total there, passing of course that point. So in a sense, of course at A, at that ammeter, they would have I total. So again, of course, at that point would have of course I total. But when it gets to that node there, to that point B, in this case, of course some of the current would go that direction, and of course some of the current would continue to go that direction, right? So would have I1, and of course would also have I2. So this is of course where our current splits. Now remember we said of course resistors that are parallel to one another, they split, they divide the current, right? So of course that's one thing that we mentioned. So of course if we look at question 7.1, this is that calculate the total effective resistance between A and B. Where is A and B? So we have A there and we also have B at that point, right? So in this case, they are saying that calculate the equivalent resistance, of course, of our parallel resistance. So again, of course, to calculate that 7.1, I'm going to write that there, 7.1. Now I'm going to continue with the other questions, of course, on the other paper. So of course, to calculate the total effective resistance across these 2 points, I can note that of course that those are resistors that are parallel to one another, right? So of course to calculate the resistors that are in parallel, that are parallel in this case, so I would use 1 over R parallel would be equals to 1 over R1 plus 1 over R2. But note, these two resistors, I'm going to treat them as 1. So in this case, this would actually be 1 over R4 plus 4 plus 4 plus 1 over R2. That R4 resistor there, that R4 ohm resistor. So again, we would note that this would actually be 1 over 8, right, plus 1 over 4. So this would be actually 1 over R parallel. And of course, to get our R parallel in this case, what we're going to do is that you can take 1 over 8 plus 1 over 4. And of course, we're going to invert that. And what the value that, of course, you are going to get, if you put that in your calculator, you're going to get a value of 2.67. If you round that off, it's actually 2.66667, but of course if you round that off, this will actually be 2.67 ohm. So that would be the effective the total effective resistance between A and B. So that was actually given to be 3 marks. I don't know, yeah, that was actually 3 marks there. So of course now they say that of course, as we can note that of course our current was not flowing, because we note of course that switch there was open, right? So that was actually S. So that was switch S. So of course, so they say that when switch S is closed, the ammeter reads 2.57. So so now we have actually closed that switch. We have actually closed it. Now of course our current will start flowing. Right now they are saying that of course the ammeter reads of course the current of 2.57. so our current at that point of course on that ammeter would be 2.57 amperes. So of course we can know that of course when our current gets to that point, some of it will split to that, and of course some of it will of course split to that direction. So they said that of course calculate the resistance, and I'm going to continue even on that part there that I have there. So they say that of course calculate the resistance of R. Now in that formula that I showed you, the Ohm's law formula says which said of course I was equals to V over R. They can actually ask you any variable there. So they can actually give you the current, the total current, and they can actually give you the total voltage, and then it requires you of course to calculate the total resistance. They can actually do that, and of course they can ask you any variable there. They actually can ask you any variable. So if of course we check at that question that we have there, they said of course calculate the resistance of R right now, but where is our R? That would be our R there. Now remember, we have actually calculated the effective resistance across of course these two these branches, right? And we found that to be 2.67. so in a sense of course that 2.67 would actually be in series with that of course with that resistor there. So that's of course one thing that you must note. So the first thing that you are going to do there, there are actually 2 ways you can actually choose to do that. The first way, in this case, I'm just going to show the other way, of course, in the next on the other paper. So the first way we can do that, we can note that of course they gave us, we have of course the total voltage, But what do we also have? We actually have the total current. So in this case, we can actually use Ohm's law to calculate the what we can do in this case, we can actually be able to calculate our total resistance. All right, so if we do that now, I'm gonna tell you why I actually did that. So in this case, this would actually be I would be equals to, of course, to V divided by R, but that's R total, right? So that would also be, of course, RT, and that would also be IT. So of course, in this case, that would actually be 2.57. That would actually be equals to V. Now that's my V total, so that would actually be 12. So this would be 12 divided by R total. All right, so of course, if I do my mathematical gymnastics there, so RT would actually be equals to that 12 divided by 2.57. So if you put that in your calculator, you're going to get a total effective resistance of course, of the whole circuit. So that would actually include that R plus that of course, that R parallel in this case. So now remember, we said, of course, if we use that voltage there, in this case, we would need to use the effective resistance, right? So in a sense, we have actually found the effective resistance. So we'll find that to be actually 4.66926. Now unfortunately, you can't round off early because it's not the final answer, right? So this would be, of course, RT. But now remember, we know, of course, that to get R total, we would actually need to take the R parallel plus that resistor there. So of course, what we can note again, so this would actually be 7.2.1. So of course, we can note now there is another way we can actually use to calculate R total. So in this case, we know that, of course, R total is actually equals to R parallel plus R series, which is actually that resistor there. But remember, we now have R total. So actually that R total, they would actually be 4.66926. That actually be equals to R parallel. We found our R parallel to be actually 2.67, right? So this would be 2.67 plus that resistor there that we don't know its value, right? So of course, to find that R, what you're going to do is that you're going to transpose that 2.67. So in this case, you have actually your R being it's actually if I round that off, you're going to get a value of 2 ohm. So that would be, of course, the value of that R. So the first thing that you needed to notice that they gave you the total voltage, right? But they also gave you the total current. So in this case, we were able to find the equivalent resistance across our circuit, right? But at the same time, we didn't know, of course, at the same time, the other way, we would be able, of course, we would have, of course, calculate that R total was to take our R parallel plus that resistor there that we didn't know of, right? But now since, of course, we have R total being that, and of course we have R parallel, we would of course have one unknown. In this case, we'll calculate it, of course, in that way. So I'm going to calculate that 7.2.2 again. I'm going to come back at that second way. I said, of course, there is another way that we can actually be able to do this. So I'm actually going to do it after I've done that question, because in a sense they're kind of connected at some certain point. So of course, that question there, they said 7.2.2, they said that calculate the potential difference over the resistor R. So what they want, of course, is the voltage across that R resistor, which we found to be 2 ohm, right? So in this case, this is actually 2 ohm. What am I doing? This is actually 2 ohm. So that would be 2 ohm there. But we know, of course, that the current, now remember, when it gets to when the current gets that node, it splits. But when it gets to that point A there, it joins again, right? It becomes 1. So in this case, of course, the current that will be passing that R would actually be I total, right? So this would be actually I total. but we know that of course I told that was 2.57. So what we're going to do, let me just again squeeze that down there. Forgive me, ladies and gentlemen. So this would actually be 7.2.2. So again, we know that we know the resistance of that resistor. All right, we know the current, but in this case, what of course they want would be the potential difference. They want actually the voltage across that resistor R there. So what we're going to say, we're going to say I is equals to of course V divided by R. And of course, we know the current, right, to be of course that 2.57. Of course, we are looking for the voltage, right, the potential difference, so that we leave that as open. But we know the resistance of that resistor to be of course 2, right? Of course, if you cross multiply there, you're going to find your V, the voltage, being let me just put that in my calculator. Let's see what the value that we get. So of course, you're going to say 2 multiply by 2.557, and you're going to get a value of 5.14. So you're going to get 5.14. That's the value that I get there. So this would be of course 5.54 volts. So that of course would be the potential difference across that across that 2 ohm resistor. Now another way, let me just go back to that. So another way that you could have chose to do that question was to say right now, remember we said of course when the current gets to that point, it splits, right? So the first thing that I did, the first thing that we did, now remember we said of course the current across that that point there was actually 2.57, right? So one thing that I did was to calculate the potential difference across my parallel resistance. So I can now remember, of course, that if we calculated the effective resistance, right, across our parallel resistance, and we found that to be 2.67, right? So what I did was to calculate the potential difference across those two parallel resistance. So what I said was that I said, of course, I is equals to V divided by R. Alright, R parallel. So this would actually be V parallel. So now remember, of course, when I combine when I combined these two resistance, what I'm going to get in this case, now remember we still had we had R there, all right? But when we combined those two resistance, these two branches, we got that to be 2.67, if I'm not mistaken. Let me check again. So that was 2.67 ohms. So that was, of course, when we combined those these two branches. So what I did was to calculate the voltage across this R parallel. Now remember that, of course, the voltage, the current that would be passing through that resistor, they would actually be R total, right? So in this case, we would know the current that is passing through our R parallel. So what I did was to calculate the voltage across our R parallel. Now remember, I know, of course, the current. I know, of course, that the value of R parallel. So what I did was to say this would be, of course, 2.57. That's my current. So this was equals to V parallel, of course, divided by that 2.67. So I found my V parallel to be let me just put that in my calculator. So that I found that value today to be 6.8. Yeah, I'm not gonna round that off. Actually, I'm just gonna leave it as it is. So that's actually 6.8 619. So this was 619. Unfortunately, I can't round that off. Why? Because of course this is this is not the final answer. So again, so what I did was, of course, now remember I know, of course, the voltage across this our R parallel, right, to be, of course, in this case 6.8619. Yeah, that's the value there. Now remember that, of course, the voltage that was supplied by our battery, they said that was 12 volts, right? So but now remember, of course, that 12 volts there would actually be distributed to our parallel, right? And of course that unknown resistor there. So of course I know I would know in this case that, of course, my V total would actually equals to the voltage that is distributed across my other parallel, which would of course be V parallel, plus the voltage that is actually distributed to that resistor there, which was actually V. I'm just going to leave that as R. So I know my total voltage, right, the voltage that is supplied by the battery to be, let me just bring that down there so that's visible. So again, we know our V total to be of course 12. So now remember, I found V parallel, right, to be of course 6.8619 plus my VR, right? But now remember, as you can note, I actually have one unknown there, of course, to find the voltage that is actually used across that unknown resistor. So in this case, I know that of course this would be a VR would be equals to 12 minus that 6.8619. Of course, if you put that in your calculator, you're going to get a value of 5.1381 volts. So that would be the voltage that is actually used by that unknown resistor. But now note, what do I have about that unknown resistor? I don't know, of course, the resistance of that resistor, but I know that the current that is passing through that point would be the total current. All right. And also, what do I know? I actually know the voltage that is actually used by that resistance. So in this case, I can actually be able to use Ohm's law. So I know that of course that I is actually equals to V, all right? Of course, that is used by that resistor. Divide that by R. Of course, that resistor there, that is unknown. Now, as you can note, I have of course the current that is passing through there. It will be the total current, right? Because it actually meets the current there, it meets that point. So that the current that splitted, that was of course traveling in that direction, I'm just going to call that I1, and the one that of course was passing through that would actually be if we of course if I put those together, it would actually be that would actually be I total, right? So of course when it gets to that point, this is of course when these two current, so that's I1 and I2. So when of course when they get that point, this is of course when they meet. All right, so this is of course where they meet. They are actually 2.57 again. So of course I know that that current there would be 2.57, so that would equals to VR. Now VR, I found that to be 5.131 point of course 5.1381. So of course that would be 5.1381. Divide that by R. So of course find R in this case, would know that of course that R would actually be equals to 5.13881 divided by 2.57, and let me just press that on my calculator. Let's see what we get. So we have that to be 5.1381 divided by 2.57, and what you can note that of course we have a 1.999. Of course, if you round that off, you actually get a value of 2 ohm. And again, you can see that we arrive at the same answer, ladies and gentlemen. We found that of course to be our of course that 2 ohm, right? So in this case now, if of course you check it that following question, let me just take that paper again. So if you look, of course, at the following question, they say that calculate the potential difference over the resistor R. But as you can note, I've actually calculated it there. So of course, if you have if you had done that if you had of course done that question in this way, what you would have done for that second question was to say that so that was actually, let me take that paper again. So of course in this case, in answering of course 7.2.2, you would of course say that you would actually just, you can write it again, but you can just say that of course VR in this case would be 5. Of course if you round that off, it would actually be 1.14 volts. So that was actually the value that we got, right? Yeah, that was actually the value that we got. So that was going to be 5.14 volts. So you would say that that value is 5.14 volts, and you can just write that proven above if you want, or you can just simply say refer to the to of course refer to that question there, which is actually the one that was, which was 7.2.1. You could have just said referred to 7.2.1. So that would be, of course, for that question. So that was actually how many marks? So this was actually 2 marks, of course, the last one. And of course, the 7.2.1 was actually 4 marks. So that's how you could have, got those marks. So we're going to look at another question, and yeah, I think that, might conclude it. So that's we're going to do question 7. Again, I sourced it from a past paper. They say that in the circuit below, the battery has an EMF of 12 volts. The resistance of the wires may be ignored, meaning that, of course, the wires would not use any of the of that energy, of course, that which was provided by the battery. They said that switch S is closed, meaning that, of course, there is current passing through. So they said, of course, 7.1, they said that define the term electric current. So electric current, by definition, we say that's the electric current is actually the rate of flow of charge. So that's the definition of it. That's how you could have got that 2 marks. So if we look at 7.2, I'm trying to rush, this video is already a long one. They said that calculate the reading on the ammeter. Now where is our ammeter? So that would be our ammeter there. But not let me just continue reading. Of course, you must finish reading the statement, ladies and gents. They say that the switch S is closed and the reading on V2, where's V2? So this would actually be our V2. They say that this is actually 3 volts. So that's the voltage that is read, of course, across our of course those resistance there. So of course, so what we're going to do again, so in answering that 7.2, what we're going to do, that they said, of course, calculate the reading on the ammeter, right? So what are we given there? Now, of course, where's our ammeter? So there's our ammeter there. Now remember, now, of course, an ammeter, of course, it reads a current. So the current that would be passing through that point would actually be I total. All right. So of course, what they're asking us there is that I calculate I total. But remember, which current would be passing at that at 6 ohm resistor? It would actually be I total. All right. But note, what am I given? I'm actually given that these resistors that are parallel, that are in parallel with one another, they're actually using 3 volts. So now remember, we said, of course, we know that V total would actually be that voltage there would actually be some of it would be used by this by these resistors, and what's left would be using by that 6 ohm resistor, right? So of course I would be able to know that, of course, V total in this case would be equals to V of course 6 ohm, right? The voltage that is used by that, plus the voltage that is used by our parallel resistance, which they gave us to be 3 volts. So of course you can note I have my V total, all right, to be 12, to being 12. Of course this is, of course, 7.2. I have that to be 12, and of course the voltage that is used. What I'm trying to achieve is that I'm trying to calculate the current that is passing through that 6 ohm resistor. Of course it would be the same, right? It would be the same current that is passing through that ammeter there. Now the reason why I'm actually avoiding using Ohm's law is because, if now remember, if I use the 12 ohm resistor, that 12 volts there, I would need to use the equivalent resistance in our circuit, right? But you can note that I actually have an unknown there. So in this case, I would have R that is an unknown again in one of in the equation, but I would also have the current as an unknown. So what I'm trying to do is I'm trying to find the voltage across that resistance. So if I know the voltage across that resistance, now remember, I know the resistance of that resistor to be 6. So in this case, I would be able to calculate the current. So that's what I'm trying to achieve there. I'm trying to calculate the voltage that is actually used by that 6 ohm resistor there. So of course we know that this would be V 6 ohm plus our V parallel. They said that, of course, that's 3 volts, right? So that would be, of course, the voltage that is used by this resistor there. So of course this would be V parallel. So again, this was given to be 3, and again we can note that V 6 ohm would be equals to 12 minus 3, which is actually 9 volts. So this 9 volts would be the voltage that is actually used by that by that by that 6 ohm resistor. So of course in this case I actually know V1 to be of course that 9 volts, right? But again, now remember, now I could actually use Ohm's law to calculate that the total current there, because now I know that the current that is passing through that 6 ohm resistor would be the total current. It would be the total current, which would be of course the same current that passes through that that ammeter reading there. So what I'm going to say is that I in this case is equals to, remember I'm still answering 7.2, so that's I is equals to V divided by R. Now remember, if of course I'm using that voltage there, I must use it with its corresponding resistor, right? And that which of course resistor would that be? Of course I'm sure you're saying that's of course that 6 ohm resistor. So of course now remember I'm looking for I, so this would be equals to the voltage, which is actually a 9, right? And I would divide that of course by 6. And of course if you put that in your calculator, you're going to get, so 9 divided by 6, you're going to get a value of 1.5. So our of course our total current would actually be 1.5 amperes. So that would be of course the current that is actually passing through that that point there. So that would be of course the answer for that. So 7.3, they said that calculate the total resistance of the circuit. Now again, remember, that's actually 2 marks. As you can note, I'm sure some of you are saying, how is that possible? Because we have that to be unknown there. Now remember, we said of course, if we, and I'm just gonna write that, let me just write that down there. Let me just write that there. So now remember, we said of course we have Ohm's laws formulae, which says of course R, which says of course I is equals to V, of course divided by R, right? Of course if we modify that. So again, if now remember, now we know the total current that is passing through our circuit to be of course 1.5, but we also know the total voltage that is actually distributed to our external circuit, to our circuit, in this case to be 12, right? So of course the equivalent, so this R in this case would be the total resistance of our circuit. So what I'm going to do is say, right, so we know that of course the total current, so this would of course would be of course V total, and also this would be of course that that R total, and of course that would also be that the I total. So we know of course I total, that would be 1.5, that would equals to V total, they gave us to be 12 volts, so this would be 12 divided by R total, right? Because that's what they want there. So in this case, if you do your mathematical gymnastics there, you would actually find R total to being 12 divided by 1.5, and of course if you put that in your calculator, you're going to get a value of, let's say, 12 divided by 1.5, and you're going to get a value of 8. So you're going to get, a value of 8 ohm. So that would be that would actually be the R total. So that would be the equivalent resistance across our circuit. So that would be our R total. So again, let me just, I'm just gonna write that on the next slide. So question 7.4, they say that calculate the resistance of R. So of course we're going to do that. So that's what we're going to do there. Now remember, so that's actually 7.4, right? So that's 7.4. So what we're going to do there is that now remember, we know the voltage that is actually we know that V2 in this case that's 3 volts. Of course we know that but remember, we know that of course the current that is distributed there would be of course our total current that was. Now remember, we said of course some of the current would go that direction, of course some of it would go that, and of course some of it would go there, and of course they would meet when they get to that point there. So what I'm going to do there is to say, right, so the first thing that I'm going to do is that I'm going to combine these two resistors there to treat them as one, only these two. So when I combine those two resistors, they would actually become one resistance. They would actually become as one. So of course, in this case, they would be in a sense look like this. So we would have to have that R, right? Would have that R. Forgive me about that ugliness there. And of course we would have that R parallel when I combine those two. So what I'm going to do, I'm going to calculate my R parallel, but only using these two. So in this case, I would know that of course R parallel But remember, only through for this, right? So this would actually be 1 over R parallel. So that would actually be equals to 1 over R1, right? Which is that plus 1 over R2. Now I'm gonna tell you why I'm doing that. That would actually be equals to 1 over R4 plus 1 over 6. Now, of course, to find R parallel in this case, we would actually take that, of course, we invert it, right? Multiply that all of it by, of course, -1. And of course, if you put that in your calculator, you're going to get a value of 2.4 m. Of course, that ohms. So this would actually be for 2.4 ohms. Now I'm gonna of course tell you why I'm actually doing that. So what I'm going to do right now is that I'm going, now remember, I know of course the total current, right? I know that of course I, in this case, that would actually be, found that to be, let's say that was actually 1.5. So what I'm going to do then to calculate that R, not complicating things, I'm going to calculate the current that is passing through that 2.4 ohm resistor. So if I know the current that is passing through that 4 ohm resistor and I know the total current, so in this case, to find the current that is passing through that point, I would actually I mean the current that is passing through that that unknown resistor would actually be equals to the that of course we know of course that I total would actually be equals to the current that is passing through that 4 ohm resistor, right, plus the current that is passing through that unknown resistor. So in this case, what I'm going to do now, I'm going to calculate the current that is passing through that my R parallel, right? But remember that of course we know that now remember the voltage that of course would be the voltage of course across our R parallel in this case would actually be that 3 volts right now. Remember, of course, we see that the resistors that are parallel to one another, of course, they have the same voltage, right? So what I'm going to do is to say, right, so in this case, of course, now I would know the voltage across my my 4 ohm my 2.4 ohm 2.4 ohm resistor, right? So what I'm going to do, I'm going to use Ohm's law, which says of course I is equals to V divided by R. Now remember, what I'm trying to achieve, I'm trying to find the current that is passing through these two, right, when I combined them. So in this case, I know that of course the voltage that is passing through those would actually be that 3 volts, right? Now remember, of course, they have the same the voltage. So what I'm going to say is that I in this case would equals to the voltage, in this case that's 3, so this would be 3 divided by my R. So in this case that would actually be that 2.4. So this would be 2.4. Of course, if you put that in your calculator, what you're going to get there would be 1.25. So this would be the current that is passing through my passing through this two resistance there. So this would be of course my I. So the current that will be passing through that point would actually be 1.25. But remember, we said that of course I total, right, would equal to, now of course, now remember of course we said that current, when it gets to that point, it will split, one of it some of it would split to those two, right, when combined, and of course some of it would split to that would go to that R there. So I know that of course I total would actually be equals to I, of course the one that is equal to R, and of course plus my R my I, of course, of that parallel R parallel. So of course I know my total current to be 1.5, all right, and of course my R IR, that's what I'm trying to achieve, right, plus of course I know the current that is passing through my parallel resistance, those two, to be of course 2, that was actually 1.25, so that would be plus 1.25. And of course if I'm trying to if I calculate that the current that is passing through that unknown resistor, of course IR would actually be equals to 1.25 1.5 minus the 1.25, so you'd actually get in a value of 0.25 amperes. So that would actually be the that would actually be the current that is passing through that unknown resistor there, right? But remember, we know the voltage that is actually passing through that unknown resistor there to be 3. Now remember, of course, we said that the resistors that are parallel to one another, they have the same voltage, right? So that's one thing that you need to note. So of course, if you note now, what do I have across that that unknown resistor there? I know the current to be, of course, to be of course that 0.25, and of course I also know I know that V in this case is actually that 3 volts. So what I'm going to do is I'm going to use Ohm's law. So I know that of course I is equals to V divided by our R. Now of course I'm going to use the voltage across that unknown resistor there. We found that to be 0.25, right? So this would be actually so the voltage in this case would be 3, right? But our R in this case, that's what we are looking for. And of course the current, of course we found that to be 0.25, right? So this would be 0.25. I think I'm actually making a mess. I in this case would actually be equals to V divided by R. So in this case my I will say that's 0.25. So this equals to 3 divided by R. Of course, if you do your mathematical gymnastics there, you're going to find your R to be, let's see. So this actually I found that to be actually 12 ohm. So that would be of course of course, so that resistor there would actually be 12 ohm resistor. So that would be of course would be the resistance of that resistor. So that was actually a question. Let's see. So that was of course that question. So that was actually that 7.4 there. So that's how you could have got those that 4 marks. So the first thing that you would have done was to calculate the current that is passing through those two. Now if you of course the total current, you actually take the total. So find the current that is passing through R. You would take the total current, and of course you will subtract the current that is passing through these two, and then of course you'd get the current that is passing through that unknown resistor there. So of course 7.5, they say that if the resistor R is removed from the circuit, what would happen to the reading on V1? Now that question, I don't want to lie to you, ladies and gentlemen. I kind of don't like the way they ask these questions. Why? Because they're actually asking me to make a prediction and then explain it. So what I like to do is that I just answer the following that second question, and of course I just go back to it. So of course if of course we answer that 7 point, let's see, do you have another page there? Let me just write it on that page. Of course that would be, of course, let me take that question again. So that's 7.5. So if we look at 7.5, let me just take that again. So of course they said that of course if resistor R is removed from the circuit, what would happen to the reading on V1? So what we have done here, they've actually removed this resistor there. All right, they actually removed that resistance there. So remember that of course now what's going to happen to that resistance? So what would happen to the value of V1? It would actually decrease. So in this case V1, I'm gonna explain to you why. So V1 would actually would decrease. I'm gonna tell you why that's the case. So of course when R is removed, the total, now remember when of course we remove that R there, the total resistance of course across our branches in this case would actually decrease. Now remember we found that the resistance across those two resistance, let me just take that back. Now we found of course the resistance, the equivalent resistance of these two to be, that was actually what value did we get there? We found that to be 2.4. All right, that was actually 2.4. Yes, so that was 2.4. So what I'm going to do right now is that I'm going to calculate what would be of course the effective resistance across all of these three resistors. So what I'm going to do, I'm going to say R parallel is equals, I want to know what would happen of course to my current on those branches there. So of course now if of course to calculate R parallel again, so this will be R1 plus 1 over R2 plus of course 1 over R3. So of course if I do that, so this would be 1 over that 4 plus 1 over 6 plus 1 over that what's that value there? We said that that value was actually 1 over 12. So if you put that in our calculator, let me just quickly find that value. So we have 1 over 4 plus 1 over 6 plus, of course, 1 over 12. Just gonna invert that immediately. So it's -1 there. So we actually find the effective resistance across those three to be actually, so R parallel in this case would actually be equals to 2 ohm. Now note, so that would be the equation, so that would be my R parallel when there is that third resistance there. But if I remove that third resistance there, that R, you would know that of course my resistance in this case would increase, right? So it would actually increase from, now remember, we have that we, of course, we know that R parallel was actually 2 ohm, right, when there was that third resistor there. But if we remove that, would actually get the R parallel, the new R parallel through my on those two branches, it would actually be, we found that to be, where was it, to be 2.4. So if I remove that resistor there, my resistance across my branch would actually increase, right? But if you note, if we look at that question there, which says I is equals to V divided by R, right? So if of course I'm looking at the current, now I'm going to only to use current. Why? Of course that's the case. Why I said of course the voltage across that V1 actually changes. So if of course, now remember, if I remove that resistor, my resistance in this case would actually increase, right? In this case my R parallel will increase, right? So if my resistance there increases, that would actually tell me that that current there would actually increase. So in this case I know that of course so an increase, so if of course R is removed, so in this case that of course my resistance would increase, right, across that those R parallel. So my R parallel in this case would increase, but an increase in R in resistance would actually tell me that of course that current would actually decrease. So if that current decreases, so that would mean that of course the current that would come out there would actually be a smaller current, right? So that would actually mean that of course my current would actually, my total current would actually decrease. So that would actually mean that my I total would decrease, right? So that would actually tell me that of course my my total current would actually decrease. Why? Because in this case my resistance increases, so right? So an increase in the resistance, that would cause my my current to decrease, right? So in this case if R is removed, the resistance would increase, right, of course, on those branches, but that would actually cause the total current to also decrease, right? But if my current increases, again I'm going to take the same formula. So of course I'm going to modify it, of course, making that V the subject of the formula. So in this case we know that V of course would be equals to that it equals to my I, of course, multiplied by R. So now remember, if of course my total current decreases, that would actually cause my voltage there on V1 to decrease. So of course so that would actually mean that of course my voltage V1 would actually decrease. Why? Because in this case my total current in my circuits decrease. So an increase, of course, so an increase in resistance would actually cause the current to decrease. But if the current decrease, that would actually mean that of course my voltage in this case would also decrease. Why? Because if we look at that equation there that I modified there, we know that of course the current in this case is actually directly proportional to what? To our voltage. So that would actually be of course the answer for that. So in this case V1 would actually decrease. So I would suggest that of course you go through this first, and then after that you actually go back to answering that question, because it's kind of it confuses that you answer a question not knowing what the outcome would be. So this is of course the end of today's lesson. Of course, there is another question which I'm not gonna do because I don't want to make this video the longest, even though it's already 1 hour and 30 minutes. So yeah, so this of course was the other question. So I would ask you to do to attempt this question, and you can always just throw the answers in the comment section. I hope I've been able to help at some extent. So yeah, this is the end of today's lesson. Of course, if this video helped you at some extent, be sure to hit that like button. And also, if you have any question, you're more than welcome to ask in the comment section. Of course, if you have any topic that you would love me to cover next in the physics part, you can always just throw that in the comment section. But otherwise, it has been very fun. But this is the end of today's lesson. So this is Sir Mike signing out. Sharp, sharp.